Hello, in this lecture we will find the radius of the small circle. In the drawing we have two circles with an internal lunge between them at this point. Let's define this point as point N. Point N is the point of contact between the two circles, and actually the small circle has three tangents. This is the first tangent, so the line segment is tangent to the circle at this point. Let's define this point as point S. So the line segment is tangent to the circle at point S, and then we have the second tangent to the small circle at this point. Let's define the point of contact between the tangent and the circle as point Z, and there is a second tangent to the small circle at this point. Let's define this point as point M, and we also know that AC equals to 9 units and BD equals to 4 units, and this is a right angle, and this is also a right angle. It equals to 90 degrees, and we want to find out the radius of the small circle, this small circle. So first of all, let's define the center of the small circle as point Q, and we will define the center of the big circle as point P. Okay? So I'll write it down. Q, point Q is the center of the small circle, and point P is the center of the big circle. Okay? Point P and point Q. Point P is the center of the big circle. Okay, again, point Q is the center of the small circle, and point P is the center of the big circle. Okay, and we will also define small r. We will define small r as the radius of the small circle, and we will define capital R as the radius of the big circle. Again, small r is the radius of the small circle, while capital R is the radius of the big circle. Okay? In the next step, we will draw three radiuses of the small circle from the center of the circle, that is to say from point Q to the point of contact between the tangents to the circle. So we will draw this radius So we actually draw the radius from the center of the circle until it touches the point of tangency with the tangent at this point. So actually we have a rule number 1, that states according to rule number 1, the tangent to the circle is perpendicular to the radius drawn to the point of tangency. So I will read rule number 1 again. Rule number 1 states that the tangent to the circle is perpendicular to the radius drawn to the point of tangency. So actually here we have a radius that is drawn to the point of tangency, because the radius starts from point Q and ends at point S, and point S is the point of tangency between the tangent to the circle. So the radius is drawn to the point of tangency, therefore it is perpendicular to the tangent. This is the tangent to the circle, and the radius is drawn to the point of tangency, therefore the radius is perpendicular to the point of tangency. So this is a right angle. Okay? And we will, in the same way, we will draw the second radius of the small circle to the point of tangency, point Z. Point Z is the point of tangency between this tangent to the circle. Therefore, according to rule number 1, the radius is perpendicular to the tangent when it is drawn to the point of tangency. And indeed, the radius is drawn to the point of tangency, that is point Z. Therefore, the radius is perpendicular to this tangent. Okay, and in the same way, we will draw this third radius to the point of tangency, that is point M. Point M is the point of tangency between the tangent CD to the circle. Therefore, the radius is perpendicular to the tangent when the radius is drawn to the point of tangency, and indeed the radius is drawn to the point of tangency, that is to say to point M, and therefore the radius is perpendicular to the tangent CD. Therefore, this angle is a right angle, it equals to 90 degrees, and also this angle is a right angle, it equals to 90 degrees, according to the rule that the tangent to the circle, that is to say CD, is perpendicular to the radius drawn to the point of tangency. This radius is drawn to the point of tangency, that is to say to point M. Therefore, the tangent to the circle is perpendicular to the radius. So this angle is 90 degrees, and also this angle is 90 degrees. And also here, the radius is drawn to the point of tangency, therefore it is perpendicular to the tangent. And here also, this radius is drawn to the point of tangency, that is to say, the radius ends at point Z, that is the point of tangency between the tangent to the circle. Therefore, this angle is a right angle. Okay? And we also know, according to what is given us in the question, that this is a right angle, so this also must be a right angle, because along a straight line in the upper side, the sum of the angles is 90 degrees. So if this angle is 90 degrees, this angle is also 90 degrees, and also this angle is 90 degrees. So this angle also must be equal to 90 degrees. Okay, so actually we have in the quadrilateral, in this quadrilateral, we have 4 angles that equals to 90 degrees. So in QZMD, QZMD is the quadrilateral with 3 right angles. Okay, QZMD is the quadrilateral with 3 right angles. With 3 right angles. And we have also rule number 2 that states that the sum of the angles in a quadrilateral is equal to 360 degrees. Again, rule number 2 states that the sum of the angles in a quadrilateral is equal to 360 degrees. Again, according to rule number 2, the sum of the angles in a quadrilateral is equal to 360 degrees. So in quadrilateral QZMD we have three angles that equals to 90 degrees. So the fourth angle must be equal to 360 degrees minus 3 times 90 degrees. That is to say, the fourth angle must be equal to 360 degrees minus 270 degrees. That is to say, it must be equal to 90 degrees. Okay, so we proved that this quadrilateral has 4 right angles. Okay, we proved that quadrilateral QZMD has 4 right angles. Therefore, according to rule number 3, rule number 3 states that if a quadrilateral has 4 right angles, then it is a rectangle. So according to rule number 3, if a quadrilateral has 4 right angles, then it is a rectangle. So we actually proved that quadrilateral QZMD has 4 right angles. Therefore, a quadrilateral QZMD is a rectangle. Okay, so QZMD is a rectangle. Okay, QZMD is a rectangle. And we have rule number 4 that states that the opposite sides of a rectangle are equal to each other. Okay? The opposite sides of a rectangle are equal to each other. Okay, rule number 4 states that the opposite rule number 4 states that the opposite sides of a rectangle are equal to each other. So here QZ is opposite to MD, so QZ equals to MD according to rule number 4. QZ that is opposite to MD is equal to MD, so we can write down that QZ equals to MD. QZ equals to MD, so but QZ equals to small r, QZ equals to small r. Therefore, from this equality we can deduce that MD also equals to r. Okay, MD also equals to small r. Therefore, here we can write down that MD equals to r. MD equals to r. Okay, then we will repeat on the same process on quadrilateral SQCM. Okay, in quadrilateral SQCM we have three right angles, 1, 2, and 3. All those three angles are right angles. This angle is a right angle because it is given us in the question. This is a right angle because the radius is perpendicular to its tangent, and this is a right angle because of the fact that the radius is perpendicular to its tangent. So in quadrilateral SQCM we have three right angles. Therefore, according to what we did in this quadrilateral, we proved that whenever you have a quadrilateral with three right angles, then the fourth angle must be equal also to a right angle. Therefore, the fourth angle must be also equal to 90 degrees. So this is also a right angle. Therefore, quadrilateral SQCM that has four right angles is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. So SQ that is opposite to CM, those sides are equal to each other, and SQ equals to R, so CM also will be equal to R, exactly the same process as we did in this quadrilateral. So CM equals to small r. Okay, I don't want to repeat on the same process on this quadrilateral because it is exactly the same proof that CM also equals to R, so I will not repeat on the same proof. Okay, so In the next step, we will define PM as X, PM equals to X, so CP equals to CM minus PM, okay? CP equals to CM minus PM. Very simple. CP equals to CM minus PM. Okay, so CP equals to CM, that is R, small r, minus PM that we defined as X. So actually CP equals to R minus X. Okay, CP equals to R minus X, and now we will calculate the value of the big radius of the big circle. We will calculate. We have already know that AB equals to, is the diameter of the big circle. It equals to 2R. So this is AP equals to R, and PB also equals to R, a capital R. So we will calculate the value of AP. Actually, AP equals to AC plus CP. Okay, AP, that is the radius of the big circle, equals to AC plus CP. AP, that is the radius of the big circle, equals to AC plus CP. Okay? Again, AP equals to AC plus CP. Okay? But we know that AC equals to 9 units, and CP equals to R minus X. So the radius, it will be equation number 1, capital R of the big circle equals to 9 plus R minus X. In the next step, we will calculate the radius of the big circle from this side. The radius of the circle is also equals to PB, because actually AB is the diameter of the big circle. It equals to 2 times the radius of the big circle, so PB is also equals to the radius of the big circle. So we can write down that PB, this will be equation number 2, that PB actually it is the radius of the big circle. It equals to capital R. And what is the value of PB? PB equals to BD plus MD plus PM. Again, PB equals to PM plus MD plus DB. Okay, PB equals to PM plus MD plus DB. Okay, so PM, that is the radius of the PB, that is the radius of the big circle, equals to PM plus MD plus DB. Okay, but what is the value of PM? The value of PM is X according to our definition, X plus MD, MD equals to R, according to our proof that the opposite sides of a rectangle are equal to each other. Therefore, if QZ is R, then MD is also R. So MD equals to small r, the radius of the small circle, plus dB. dB equals to 4 units. It is given us in the question. So in total we got that AP, that is the radius of the big circle, equals to X plus small r plus 4. Okay? Then we can compare equation number 1 to equation number 2, because both of them are the expressions of the same radius of the big circle. So we can write down equation number 3 that states that r equals to r, the radius of the big circle, and we will substitute this r by the first equation, and we will substitute this r by the second equation. Okay, both of those equations are the expressions of the radius of the same big circle, so they are equal to each other. So we can write down that r according to equation, capital R according to equation number 1, that is 9 plus small r minus x, equals to capital R according to equation number 2, that is actually x plus small r plus 4. Okay, according to equation number 4, 9 plus r minus x equals to x plus r plus 4. Here we have r in this side of the equation, and we have r on the other side of the equation, so we can cancel r, and what is left after we cancelled r is actually 9 minus x equals to x plus 4. Okay, 9 minus x equals to x plus 4. Here we will subtract 4 from equation number 3, from this equation, and we will get that 9 minus 4 is 5. 5 minus x equals to 4 minus 4 is 0, so we left with x. So we got that 5 minus x equals to x. Here we will add x to equation number 3, to this equation. We will add x, and we will get that 5 minus x plus x is 5, and x plus x is 2x. We got this equality that 5 equals to 2x. Here we will divide this equality by 2 in order to get the value of x. Okay, so x will be equal to 5 over 2. 5 over 2 is 2.5 units. We got the value of x. X equals to 2.5 units. Okay, x equals to 2.5 units. So actually we can substitute x in the third equation of the radius by 2.5 units. Okay, we have the third equation, we have this first equation that states that capital R equals to 9 plus small r minus x. Okay, that is our first equation for the radius of the big circle. We know that x equals to 2.5 units, so we can substitute x by 2.5 units in equation number 3, and we will get that capital R equals to 9 minus x. X is 2.5 units. 9 minus 2.5 units plus small r. Okay, we got the equation number 1 that r equals to 9 minus 2.5 plus r. 9 minus 2.5 is 6.5. So in total we got that capital R equals to 6.5 plus R. So I write it down. So capital R equals to 6.5 plus small r. Okay, so we have the value of x that equals to 2.5 units, and we know that capital R, the radius of the big circle, equals to 6.5 units plus the radius of the small circle, that is to say small r. Okay, in the next step we will present a new rule, rule number 5, and we will implement rule number 5 in our circles. So what is rule number 5? According to rule number 5, if two circles have an internal lunge between them, if two circles have an internal lunge between them, then the distance between their centers is equal to the difference between the length of their radiuses. So I will read rule number 5 again. According to rule number 5, if two circles have an internal lunge between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay? So actually we can implement rule number 5 in our circles, because actually we have two circles with internal lunge between them at point N. They have point of contact at point N, so they have internal lunge between them at point N. They touch each other internally at point N. So we can use rule number 5 in our circles. According to rule number 5, the distance between their centers, that is to say, Q is the center of the small circle, and P is the center of the big circle. So the distance between their circles, that is to say PQ is equal to the difference between the lengths of their radiuses. So according to rule number 5, PQ, that is the distance between the centers of the two circles, is equal to the difference between the lengths of the radiuses of the two circles. PQ equals to capital R minus small r. Okay? So actually that is the implementation of rule number 5 in our two circles. The distance between the centers of those two circles, that is to say PQ, equals to the difference between the lengths of the two radiuses. That is to say PQ equals to capital R minus small r. So here we can add r, small r, to this equation, to equation number 4, and we will get that capital R, the radius of the big circle, equals to PQ plus R. Okay? So we found out that the radius of the big circle equals to PQ plus small r. But we have already found out, according to equation number 1, that the radius of the big circle equals to 6.5 plus small r. So we can compare equation number 4 to equation number 5 to equation number 1 and create the fifth equation that states that r equals to r equals to r. Then we'll substitute this r by equation number 1, and we'll substitute this r by equation number 4. Okay, so we will get that 6.5 plus r, that is the value of r according to equation number 1, equals to PQ plus small r. PQ plus small r. That is what we get from equation number 5. Here we have r in this side of the small r in this side of the equation, and we have r on the other side of the equation, so we can cancel r, and we will get the value of PQ after we cancelled r. Actually, we will get that PQ, according to equation number 5, PQ equals to 6.5 units. Okay, PQ equals to 6.5 units, and we have already got the value of x. X equals to 2.5 units. Okay, so in the next step we will connect together points P and Q by a straight line. Okay, we will connect together points P and Q by a straight line. Actually, P and Q, the triangle in the green color, is the right triangle, because this angle is a right angle. We have already found out that the radius is perpendicular to the tangent. So this is a right angle. So triangle PMQ is a right triangle. And we can implement the Pythagorean theorem in this right green triangle according to the, so I write it down. PMQ is a right triangle. Triangle PMQ is a right triangle. Therefore, according to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the square of the hypotenuse of the right green triangle is PQ square. PQ square equals to the sum of the squares of the perpendiculars equals to PM square plus QM square. Okay, we implemented the Pythagorean theorem in the right green triangle, PMQ, and we got that PQ square equals to PM square plus QM square. But we have already found out that PQ equals to 6.5 units, so we can substitute PQ by 6.5 and we will square it, and PM equals to X. PM equals to X and X equals to 2.5, so PM square will be 2.5 square plus QM is the radius of the small circle that we want to find out the value of it, so it will be small r squared. So okay, in total we got that 6.5 square equals to 2.5 square plus small r square. 6.5 square is 42.25 and 2.5 square is 6.25. So I write it down. So we got that 42.25 equals to 6.25 plus r squared. 42.25 minus, we will subtract 6.25 from this equality. We will get that 42.25 minus 6.25 equals to 36. So in total we will get that 36 equals to r squared. Then we will take a root out of this equality and we will get that r equals to the root of 36. The root of 36 is 6. So we got that the radius of the small circle equals to 6 units. Okay, again, the radius of this small circle equals to 6 units. Okay, so now I will summarize the lecture. So we actually wanted to find out the radius of this small circle. We have here two circles that have internal lunge between them at point N, and the small circle has 3 tangents. This is the first tangent. The tangent, this line segment is tangent to the circle at point S, and we have the second line segment CD that is tangent to the circle at point M, and we have the third line segment that is tangent to the circle, to the small circle at point Z. So we also know that AC equals to 9 units and DB equals to 4 units, and AB is actually the diameter of the big circle. Okay, and this angle is 90 degrees and this angle is also 90 degrees. So we define small r as the radius of the small circle and capital R as the radius of the big circle, and from the center of the big circle we draw 3 radiuses, and we draw the radiuses to the point of tangency of those 2 tangents. So we actually have rule number 1 that states that the tangent to the circle, is perpendicular to the radius drawn to the point of tangency. So according to rule number 1, this tangent to the circle is perpendicular to the radius that is drawn to the point of tangency. This radius is drawn to the point of tangency because this radius ends at point S, that is the point of tangency between the line segment to the circle. So the radius is drawn to the point of tangency, therefore the tangent is perpendicular to the radius, therefore this angle is a right angle. And in the same way we have actually the radius that is drawn to the point of tangency, that is to say to point Z, therefore according to Rule number 1, the tangent to the circle is perpendicular to the radius that is drawn to the point of tangency, and this radius is drawn to the point of tangency, that is to say the radius is drawn to point Z, and therefore the tangent is perpendicular to the radius, therefore this angle is a right angle. And also we have the third radius that is drawn to the point of tangency, that is to say to point M, therefore the tangent is perpendicular to the radius that is drawn to the point of tangency to the point of M. Okay, the radius or the tangent is perpendicular to the radius, or the radius is perpendicular to the tangent, because the radius is drawn to the point of tangency. Therefore this angle is 90 degrees and this angle is also a 90 degrees. Okay, so if we look at the square or the quadrilateral QZMN, we have here three right angles. This is a right angle, this is a right angle, and this is also a right angle. So according to rule number 2, the sum of the angles in a quadrilateral is equal to 360 degrees. So if we have here three right angles, then the fourth angle must equal to 360 degrees minus 3 times 90 degrees. That is to say, the fourth angle must be equal to 360 degrees minus 270 degrees. That is to say, this angle must be equal also to 90 degrees, because 360 degrees minus 270 degrees equals to 90 degrees. So we actually have here a quadrilateral with 4 right angles. And according to rule number 3, if a quadrilateral has 4 right angles, then it is a rectangle. Okay, so this quadrilateral QZMD has 4 right angles. We prove that the fourth angle is also a right angle. Therefore, this quadrilateral is a rectangle according to rule number 3. So we have here a rectangle, and according to rule number 4, the opposite sides of a rectangle are equal to each other. So we proved that QZMD is a rectangle, and according to rule number 4, the opposite sides are equal to each other. That is to say, QZ is equal to MD. But we know that QZ equals to small r, and QZ also equals to MD. So QMD also will be equal to small r. Okay, QZ equals to MD from one side, but from the other side QZ equals to small r. So we can derive from this equality that MD also equals to small r. Okay, so MD also equals to small r, and we have the same incident in the quadrilateral SQCM. We have here 3 right angles. We have already proved that when a quadrilateral has 3 right angles, then the fourth angle must be also equal to 90 degrees. So this angle is also 90 degrees. And a quadrilateral with 4 right angles is a rectangle. So SQCM is a rectangle. and according to rule number 4, the opposite sides of a rectangle are equal to each other, so SQ equals to CM. But we know that SQ equals to small r, so CM that equals to SQ must be also equal to r, to small r. So we prove that CM equals to small r and MD equals to small r. Okay? And then we defined PM as x, PM, that is to say PM equals to x, and we proved that CM equals to small r. So CP will be equal to CM minus PM. Again, CP will be equal to CM minus PM. And CM is small r and PM is x. So CP equals to CM that is small r minus PM that is x. So CP equals to small r minus x. Okay? And then, okay, so CP equals to small r minus x. And we know that AB is the diameter of the big circle, so AP equals to capital R and PB also equals to capital R. AP equals to capital R, that is to say AP equals to AC plus CP. Okay, AP that equals to capital R is equals to AC plus CP. But AC equals to 9 units and CP equals to R minus X. So actually AP that equals to R equals to AC that is 9 units plus CP that is R minus X. So R, capital R equals to 9 plus R minus X. And we also know that PB also is the radius of the big circle, so it equals to capital R. But what is the value of PB? PB equals to PM plus MD plus DB. Again, PB equals to PM plus MD plus DB. Or, in other words, PB equals to PM plus MD plus DB. Okay, but we know that PM equals to X, DB equals to small r, MD equals to small r, and DB equals to 4. So in total regards, that PB that equals to R is actually equals to X plus small r plus 4. Okay, so we got the value of capital R from equation number 2, and we got the value of capital R from equation number 1. So we can compare equation number 1 to equation number 2 because both of them are the radius of the same big circle. So we can write down the equality that capital R equals to capital R, and then we will substitute capital R by equation number 1, and here we'll substitute this capital R by equation number 2. Okay, and we got equation number 3, and from equation number 3 we got this equality that X equals to 2.5 units. But we have already know that capital R equals to 9 plus small r minus X, and X equals to 2.5 units, so we can substitute X in this equation number 1 by 2.5 units. Okay, so we substituted X by 2.5 units in the equation number 1, and we got that capital R equals to 6.5 plus small r. Okay, and X equals to 2.5 units. Okay, and then we actually presented rule number 5, and we implemented rule number 5 in our two circles. According to rule number 5, if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay, so if two circles touching each other inside, from inside, then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay, so we can implement rule number 5 in our two circles, because here we have two circles that have internal length between them at point N. They are touching each other at point N. So we can implement rule number 5 in these two circles, those two circles. So according to rule number 5, the distance between their centers, that is to say PQ, equals to the difference between the lengths of their radiuses, that is to say PQ equals to capital R minus R, because capital R minus R is the difference between the radiuses of those two circles. Okay, so we got equation number 5 that states that capital R equals to PQ plus R. But from equation number 1, we already know that capital R equals to 6.5 plus small r. So here we got equation number 5 that states that capital R equals to capital R, and we substituted capital R, this capital R, by equation number 1, and we substituted this capital R by equation number 4. And we got the value of PQ. PQ equals to 6.5 units, and we have already found out that X equals to 2.5 units. Okay, so actually we connected together points P and Q by a straight line, and here we have a right triangle because of the fact that this angle is a right angle. So the green triangle is a right triangle, and we use the Pythagorean theorem in order to find out the value of QM, that is the radius of the small circle. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say QP square equals to PM square plus QM square. Okay, PQ square equals to PM square plus QM square. We know that PQ equals to 6.5 units, and PM, that is X, is equals to 2.5 units, and the only missing variable is the radius of the small circle, that is to say small r. So we put the data inside this equality, and we got that the radius of the small circle equals to 6 units. Again, the radius of this small circle equals to 6 units. Okay, thank you very much.